Okay, Bismillahirrahmanirrahim. So let's start this lecture. So in the previous lecture we have talked about the forced vibration systems, and we have derived the response of the general forced vibrations as well as the rotation and balance. And you have seen in the last lecture that the behavior of forced vibration is quite different from free vibrations, and when the force is applied on a structure and that force must be continuous and periodic, the system responds in such a way that you have to control the frequency ratio and the damping, otherwise the amplitude goes to very high values and ultimately can destroy or fail the structure. So in today's lecture we will solve some problem from exercise as well as some sample problems, so that you can have a better understanding of what we have done the last time, because our main idea of this course is try to give you an understanding of that how we apply these formulas to solve some real systems that actually occurs in nature, and how then we can actually apply the understanding of the that we have done in the last lecture to solve different problems of the real world. So just for the sake of revision, I just write the formulas again so that you will have in your mind that which formulas we have to use in solving those numericals. So if you remember, we have studied about the total solution, which is x of t, that is equals to e minus zeta omega nt into c1 sine of omega dt plus c2 cos of omega dt, plus this is the free vibration solution. So if you remember, this is the free vibration solution or the free vibration response, clear, plus what we have is, if you remember, f naught over k divided by square root of 1 minus omega square or over omega n square whole square plus 2 zeta omega by omega n whole square square root into cos of omega t minus theta. And this is, as you know from previous lecture, is the response for the forced vibrations, as we have derived in the last lecture. We've also seen that in case of the rotation unbalance, if that force is due to the rotation unbalance, that is rotational unbalance in the shaft or a disc or whatever that is, the formulas can be slightly modified to be written as me over capital M into omega by omega n whole square divided by same whatever here in the inside the square root into instead of cos we use sine, as I told you in the last lecture that in case of the the unbalance, the sign played an important role, and we have discussed in detail in the last lecture. So it's minus theta. This is we have done last time, and you know that theta is nothing but the phase difference between the system response and the phone response, and that is equals to 2 zeta omega by omega n divided by 1 minus omega square over omega n square. And if you remember again from the last lecture that omega is your force frequency, the frequency of your force that is entering into the system, and omega n is your natural frequency. That is depends upon the stiffness. So it depends upon the stiffness and the mass. Clear? And definitely the forcing frequency does depends upon where the force is coming. Clear? So that is dependent upon the where the force is coming into your system. This is just the revision so that you are now aware of that we are using these formulas. Apart from these formulas, if you remember from the previous lecture, when we are studying about free vibrations, so we remember zeta is equals to delta over under root 4 pi square plus delta square. This also we have to use in the current numericals. Plus another formula is delta, which is 1 over n times, or in fact n minus naught times natural log of x naught over xn. So if you know the delta, just put the delta here to get the value of zeta. Zeta, by the way, is the damping ratio. Now this is we have done in the last time, and this slide is just for the sake of revision, so that you know what the formulas we have derived. The basic purpose in today's lecture is try to use those formulas to better understand how we apply these formulas to solve the real systems. Okay, so let's go towards the first numerical, and that numerical is from the exercise. So these are some basic numericals. So these are 3 numericals that we will solve. So if you look at this, I've slightly modified, slightly zoom it. So we are now solving sample problem, exercise problem 3.1. So I just solve here. So solution problem 3.1. Okay, what does it say? A part of a machine part of mass, so we know mass is 195.5 kg, vibrates in a viscous medium. Now this term is very important. Viscous means now we have a viscous damping. Clear? So what we have is the viscous damping. So that is very important in this statement. Determine the damping coefficient. Now we have to find what is damping coefficient. It's C. C is sometimes called the damping coefficient and sometimes called the damping constant. So it's the same word, either use damping coefficient or damping constant is the same. When the harmonic force of 24.46 Newton results in a resonant amplitude, and that is very important. So we have a harmonic excitation force. Harmonic means it's a periodic force, it's a repeated force. So we write here, so we have F naught, which is your excitation force, harmonic excitation force, is 24.46 Newton. By the way, if someone has a question in mind that how we measure forces, we normally, if yes, forces applied on any system, either it's a linear force or in this case an periodic or harmonic force, we use load cells. So load cells, they are available. We use load cells to measure the forces. Okay? We use load cells. Clear? So if you go to internet, you want to study about load cells, so you will find a lot of data about it. So these are very common type of instrument used to measure forces on any structure. Okay. Resulted in a resonant amplitude. Now that is very, very important word. Resonant means that your omega over omega n is equals to 1. So whenever this word came into a problem statement, there is a very clear indication, and a very, very, very clear indication that your omega over omega n is equals to 1, or in the other words, omega is equals to omega n. Clear? So it says at this force or at certain, the resonant amplitude, now we call it X, which is for amplitude, and RES for resonant, that is 1.27 centimeter. Clear? And the period is, so the period is 0.2 seconds. This is what the question is. So it demands you have to find this damping constant. Now, if you go back to the formula that we have seen in the last slide, and that is x of t is equals to f naught over k f naught over k divided by 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square into cos of omega t minus theta. This is what we have studied in the last slide or in the last lecture. Now look at what we are interested in, finding C. Now where C comes from in this whole formula? So if you split this zeta, zeta is nothing but C over CC. So now you can easily see that C is coming into the problem. Now for the amplitude, we have to, in all numericals, when you see it's an amplitude, you have to put the trigonometric term equals to 1. So indicate the max amplitude can occur when the cos omega t minus theta, whatever the values, is equals to 1. So this is equals to 1. So here, now it says it's a resonance. So resonance means if you reduce the formula, so in case of, so just write here, in case of resonance, so instead of, when you take cos omega t minus theta equal to 1, so instead of writing x of t, we write capital X, which means it's now an amplitude. Now small x of t means it's a time response, clear? It's a time response like this. When you write capital X, it means that we are only interested in the amplitude, which is maximum displacement from mean position to the extreme position. That's why we take cos omega t minus theta equals to 1. Now if you apply this capital X, so I'm just f naught over k divided by, now if you put omega over omega n equals to 1 here, equals to 1, so this whole term goes to 0, and this term also goes to 1 because omega, it's a resonance, so you end up divided by 2 zeta. I hope you understood this step. So what we have done is, I am again repeating, just we have put small x of t is equals to capital X because we are interested in the amplitude, as you can see in this is problem 3.1. When omega n equals to 1, the 1 minus 1 goes to 0, and then your omega in the second term also goes to 1, and you get zeta square cancel out with the square root, you end up divided by 2 zeta. Now I just write on the next page. So now you know that capital X, and we are resonant. Why we are resonant? Because if you remember, we have taken the resonance condition, clear? We have taken the resonance condition with the formula reduces to this formula. So it becomes f naught over k divided by 2 zeta. Or in fact, if you expand the zeta, which is c over cc, what you get is x res, which is the resonant amplitude, which is equals to, now it become f naught cc divided by 2 kc, clear? And because we are interested in c, so c is nothing but f naught cc divided by 2 k x res. I think so you have understood. What we have done is taken the c on the left hand side and taken the x rs in the denominator. So this is our relation that we have to find. This is our relation, c is equals to f naught cc divided by 2 k x res. Now the interesting thing is that when you have a resonance, so the period is given, which is 0.2 seconds. So you know that omega is equals to 2 pi by t, which is the frequency. So if you multiply 2 pi divided by 0.2, what you get is 31.4 radians per second, and that is also equals to omega n, because we know it's a resonant condition. If this is not resonance, that they cannot necessarily be equal, but because of resonance both are equal. Now you know cc is nothing but 2m omega n, as we have done when we are modeling the damped free vibrations. So cc is equals to 2m omega n. We know what m is, which is 1. Okay, what is m? It's 1.95 kg multiplied by omega n is 31.4. You get cc equals to, so multiply 2 multiplied by 1.95 into 31.4, what you get is 122.46, and the unit must be Newton per meter per second. So it's a force per unit velocity. The damping constant, it's a critical damping constant that we require to put in here. Now we don't know what K is, and that is interesting. For finding K, we know omega n is nothing but square root of K by m. So if you take square on both sides, you get omega n square is equals to K by m. So K is nothing but omega n square m. So omega n square, as we know, is 31.4 square into 1.95. You get K equals to, so we multiply 31.4 square multiply by 1.95. You get a value of 1922.6 newtons per meter. Clear? Now if you put all these values in this relation, so C is equals to, what is F naught? F naught is 24.46 as given in the numerical statement. The CC will come out to be 122.46 divided by 2 multiply, the stiffness is 1922.6 multiply by, okay, what is the resonant amplitude? It's 1.27 centimeters, so that's, you can convert it into meters. So it's 1.27 into 10 is to power minus 2. Okay? So if you just multiply 24.46 multiply by 122.46 in the numerator, and in denominator 2 into 1922.6 into 1.27 exponent minus 2, you get a value of 61.3 Newton per meter per second. Clear? So if you compare it, so just they're not requiring the numerical, but just to give you an idea. So if you divide 61.3 divided by what is CC, 122.46, you get 61.3 divided by 122.46, that is the 0.5, which means system is underdamped. As you know, it's less than 1, the system is underdamped. Not required in numerical, but just to give you an idea. Okay, so hope you understood the numerical. So as we goes on to solve other numericals, you will have a more clear idea that what we are trying to do in those numericals. So using the same formula that we have derived in the last lecture, we used in different ways to try to get different parameters that is required in the numerical. Now going towards the next problem, which is 3.2. So the problem states, that, so we are solving this numerical. If a problem in 3.1 is excited by a harmonic force of frequency 4 CPS. Now the problem is same, we know all the values. The only changing we have to now do is, now you have omega, which is now 4 cycles per second. Now that is very important point here. Now in the previous numerical we have seen that omega is equals to omega n, and that is 31.4 radians per second. Now he has changed omega. Instead of 31.4, so how we convert CPS into cycles per second? You know that omega is equals to 2 pi f, and that is 2 pi into 4. So if you multiply 2 pi into 4, what you get is 25.12 radians per second. Clear? Now the omega become different. Now we cannot change omega n. Why? Because we have not changed k. We have not changed k. We have not changed k and m. So omega n cannot be changed. and that is very, very important. So that's why you cannot change omega unless you change k and m, which is not the case in this numerical. So we have only changed omega. So it says if what will be the percentage increase in the amplitude of forced vibration when dashpot is removed. Now we have to see the increase in the amplitude when your dashpot means your damper is removed. Okay, so now there are two conditions. So say first we are interested in finding the amplitude, damped amplitude, which is this, and second is undamped amplitude. Clear? So now before solving this, we just find omega over omega n ratio for this numerical. Now I told you that omega n cannot be changed, so it's 31.4 as from the previous numerical, and now the omega is 25.12. So if you divide 25.12 divided by 31.4, you get a value of 0.8. So omega over omega n is now not equals to 1 but rather 0.8. Now the x damped is now the same, the force is same, which is, so if I again write the relation, again we don't write the cos because we taken equals to 1. So 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. This is our relation. So f naught is 24.46, the k is same, which is 1922. You see in the last slide, 6 divided by, now this is no resonance because now we have changed omega. So now the ratio is 0.8 square whole square. So it's omega by omega n, either you write omega square by omega n square or omega by omega whole square. So it's 0.8 square whole square plus 2, and you know what zeta is? 0.5 into 0.8. This is for the damped. Clear? So x damped. Why we damped? Because we're considering damping. Okay? So numerator becomes 24.46 into, divided by 1922.6. You get a value of 0.0127 divided by, and what is the denominator equals to? It's 1 minus 0.8 square whole square plus 2 into 0.5 into 0.8 square. So you get a value of 0.88. Clear? This is the denominator. If you divide numerator by denominator, so it's 0.0127 divided by 0.88, you get a value of 0.0144 meter. If you convert into millimeters, it's 1, 2, 3. It's 14.4 millimeter. This is what your amplitude when we have damped. Now in the second case, see, when the dashpot is removed, so if you remove the dashpot, so we call it undamped because there is no damping. So see, it become f naught over k divided by 1 minus omega square over omega n square. How it reduces to? Because if you look at this relation, so when you put zeta equal to 0, this whole terms vanishes, it's finished, and this square is cancelled with this square. You get only this term in the denominator, which is 1 minus omega square over omega n square, because in this case zeta is taken as 0 because it's an undamped case. If you put the values, so it's 24.46 divided by 1922.6, 1 over 0.8 square, you get 24.46 divided by 1922.6. You get a value of, again the same, 0.0127, and 1 minus 0.8 square is 0.36. So x undamped is equals to 0.0127 divided by 0.36. So get a value of 0.0352 meter. You have to convert into millimeters, you have to multiply with 1000, so 1, 2, 3, it's 35.2 millimeters. Now I just write here again, so x damped is equals to 14.4 mm and x undamped is 35.2 millimeter. If you compare both the values, you will realize that actually what happens, as you remove damping, the amplitude actually goes too high. This is what we have seen in the last lecture when we are seeing the graphs, the amplitude graphs, that if you remove the damping and you are operating near resonance, because 0.8 is very close to 1, so what happens, that amplitude goes to very high if you do not provide sufficient damping into your system. And that's why it's very important in the real life that you provide sufficient damping, so that if a system is operating close to resonance, which is omega is very close to omega n, then damping actually decreases the amplitude by a significant value. So percentage, so we are interested in the, I think so, percentage increase, yes. So percentage increase in the, so percentage increase in amplitude is 35.2 minus 14.4 divided by, I think so, 14.4. So you get 35.2 minus 14.4 divided by 14.4. So it's about, when you multiply with 100, it's about 144%, which means it's 144% more than the your amplitude that is undamped. Clear? So I hope you understood this numerical, and I'm again in this numerical what we have done, because there's a forced vibration, so we've used the same formula. One with the case when there is no damping, first is the case when they provide sufficient damping, that is the value of 0.5, as you can see here, this is zeta. So in the second case says you have to remove the dashboard, which means you have to remove the damper, which means you have to put zeta equal to 0. So what will happen then? The amplitude goes too high and you find the percentage increase, that is about 144%. Now moving on toward the third numerical, and that is again the 3.3, a weight attached to a spring of stiffness 525 Newton per meter. So we know K, which is 525 Newton per meter, has a viscous damping device. Again, viscous damping device, there is a damper which works on the viscous damping. Okay, when the weight is displaced and released, now weight is displaced and released, the period of vibration is 1.8 seconds. So the period is 1.8 seconds. And the ratio of successive amplitudes is 4.2 to 1. So successive means if you say 1 over 2, x1 over x2, so it's 4.2 divided by 1.0. Says determine the amplitude and phase when the force of F is equals to 2 cos 3t x on the system. Now one thing is very important till this statement, before this, and that is when you see a reduction in the amplitude, it means you're talking about free vibrations. Look at this, x1 over x2 is 4.2 over 1. In forced vibration, the amplitude never decays or the amplitude never decreases. So before that, we have actually tested the free vibration of the system. After testing for the free vibrations, we then apply the force to see how system will respond. So what is the importance of this? This will tell you about the zeta and the natural frequency. So say that period of oscillation is 1.6 seconds because we have displaced and released. So we know this is natural time period. So omega n is nothing but 2 pi by t. I'm again repeating, when you see a decrease in the amplitude, it means that it's a free vibration, because in forced vibrations the amplitude never decays. So divided by, and what is t? It's 1.8. So you get a value of 3.5 radians per second. So this is the natural frequency, and you know natural frequency is 2 pi by f, and f is 1 over t, so it's written as 2 pi by t. So as written here. Now these successive amplitudes are very important to determine the value of zeta. So delta is, as you know, is 1 over n, in fact n minus 0, natural log of x0 over x1, and if you see here, so it's 1 over 2 minus 1, so I have to multiply the subscript of this subscript of this minus subscript of this. This is very important. So write natural log of x1 over x2. So we have written, that's why we have written 2 minus 1 here, that's why. So it's 2 minus 1. Clear? So it's 1 over 1 natural log of 4.2. So delta will come out to be natural log of 4.2. The value is 1.435. Now we know from previous understanding, as we have done in the last lecture, when we are talking about free vibrations, that zeta is equals to delta over square root of 4 pi square plus delta square. So we have 1.435 divided by square root of 4 pi square plus 1.435 square. Clear? So we have to just write 1.435 into square root of 4 into pi square plus 1.435 square. So answer is 0.22. So as you can easily see, the system is 0.22. The system is underdamped. Clear? The system is underdamped. Now it says, now why why these three lines are written before this? Okay. That is because you don't know about the natural frequency, you don't know about the damping. So generally what happens in the real world, that when you don't know these values, you first perform a free vibration test to exactly know what is the natural frequency and the damping, and then you apply a force to see how your system will behave in us. So your force is written as F equals to 2 cos 3t, and that is a very important relation. Why? Because if you compare this with this relation, F naught cos omega t, so if you're comparing both these values, you know F naught is 2, which is 2 Newton, and omega is what? 3 radians per second. If you quickly compare those relations, you will find out that these are the values. Now I say determine the amplitude. So how we determine the amplitude? So x is nothing but F naught over k divided by 1 minus omega square over omega n square whole square plus 2 zeta omega by omega. Again we have not written cos. Why? Because cos of omega t minus theta is equals to 1 for the amplitude. Again for the amplitude. Now this is not resonance. See, so we have to first see what is the ratio omega by omega n. So your omega is 3 as from this relation, your omega n is 3.5 as we have calculated here. So 3 divided by 3.5, you get a value of 0.86. So again, it's close to resonance, but it's not resonance. Clear? So putting all these values, so you get x equals to f naught is 2 divided by nk is what we have given the numerical, which is 525, divided by 1 minus, this is 0.86 square whole square plus 2 into, so I'll just write in the next step so it's more clear of the next page. So x equals to 2 divided by 525 divided by square root of 1 minus 0.86 square whole square plus 2 into what is zeta, 0.22 into omega by omega n, which is 0.86 whole square. So 2 divided by 525, which is 0.00381 divided by, so if you divide it, 1 minus 0.86 square whole square plus 2 into 0.22 into 0.86, so that is 0.459. Clear? So amplitude is 0.00381 divided by 0.459, which is 0.0083 meter, and that is nothing but 8.3 mm. This is your amplitude. Now remember, in vibrations, the amplitude never come in orders of meters. If coming in the order of meters amplitude, then your numerical is wrong. It comes in the order of mm's or at most cms, centimeters. Not in amplitude cannot be 1 meter. It cannot be 0.5 meters. Okay? It's generally small. In most of the machines, it's less than 2 or 3 mm. But in some cases, it can be higher. Like in case of engines, it can be up to 6 or 7 or sometime 8. But it cannot. It's only 8 mm. It cannot be like 30 centimeter. It cannot be like 1 meter. Or if you're getting these values from your numericals, definitely your numerical is wrong. Clear? So you only get an amplitudes of vibrations in terms of millimeters. Okay, so what is the phase difference, which is tan inverse of 2 zeta omega by omega n divided by 1 minus omega square over omega n square, and that is tan inverse of, and what is zeta? 0.22. What is your omega by omega n? It's 0.86 divided by 1 minus 0.86 square. So theta equals to tan inverse of, so we just multiply 2 into 0.22 in the numerator into 0.86, and in the denominator it's 1 minus 0.86 square. So that's equals to 1.453. If you take tan inverse of 1.453, you get an angle of 0.96, and remember, this is in terms of radians. Why in terms of radians? Because if you look at all these values, they are in the terms of radians. Clear? So you get the angle in terms of radians. So if you multiply it with what? 180 by pi. If you multiply 0.86 by 180 divided by pi, or in simple words, it's 57.3, to you get a value of 55 degrees. Okay, this is the phase difference between the force and the motion. If you remember from the last lecture, I told you in the pre-resonance, your theta is less than pi by 2 or 90 degree, and in post resonance your angle will be greater than pi by 2. Clear? So see, this is 55 degrees, and what is your omega by omega n? It's 0.86, which means it's what? It's pre-resonance. It's less than 1. It's pre-resonance. Now your actually angle confirms. Your angle confirms that it's a pre-resonance. Although the omega by omega n value clearly indicates a pre-resonance, but you can verify it by just finding the phase angle, which is come out to be 55 degrees, and that actually says that it's a pre-resonance. Okay, I hope you understood these three numericals. These are some fundamental numericals, that is 3.1, 3.2 and 3.3 from your book. Now we are moving towards slightly numerical of the next level, or the with a slight more difficulty, and that is 3.13, and that is very important to understand. So we have a similar problem in your example as well, so we'll see later on. So this is problem 3.13 from so this is, just hold on. So this is problem 3.13. Clear? And it says that a counter rotating eccentric mass exciters. Now this is very important to mention here, that what are the counter rotating. So we have actually an exciter, and what exciter is actually, it consists of two rotating discs with the eccentric mass. Eccentric mass means an unbalanced mass located at some distance e from the rotational center. This is the rotational center of two discs. Rotation, there are two masses which are actually rotating. So just draw with the red line. So we have one mass here, we have one mass here. See, rotating. So this is generally this basically, if you look at in the diagram, this is basically your exciter. This is your exciter. Clear? This is your exciter. Exciters are generally used to test an equipment which is prone to the forced vibration. So what we do actually, let's say if you consider an aircraft wing, so when aircraft fly in the air, so you know it experiences the forced vibrations, and it vibrates because of the wind. So the frequency that wind imparts to the wing, we actually set the exciter to the same frequency and then put on the wing or the structure to see how it will respond to those frequency if it come in the from the air or any other source. So exciters are generally used to test the equipment to see how it will behave when it is actually operated in the real world. So this is what exciter is. Exciter generally has an unbalanced mass. So what unbalanced mass do? It create vibrations. It is used to determine the vibrational characteristic of structure of the mass. So we know mass is, which is 181.4 kg. This is your exercise problem 3.13 at a speed of 900 rpm. So what is the speed, which is called n1, is 900 rpm. So first of all, whenever you shoot those values, you have to convert into omega. So omega is 2 pi n by 60, if you remember from your previous courses. So 2 into pi into 900, which is rpm, divided by 60, you get the value in radians per second. So 2 into pi into 900 divided by 60, what you get is 94.2 radians per second. So remember, because formula generally has radians, so you have to convert all these, whether it's cycles per second or cycles per minute or revolution per minute, you convert it into radians per second. A stroboscope shows the eccentric mass to be at the top at an instant structure is moving upward through its static equilibrium position. So it says if this is the static equilibrium of the mass, which is says when the mass is not when the exciters are not moving, the mass is stationary, and this is static equilibrium. So when it says when this exciter mass is at the top, which is at this point, so which is at this point, that's at the top point, this mass is moving towards equilibrium position, because this mass also vibrates like this because of the force, and that force generated by this exciter. Clear? Your mass actually vibrates. So this is your task, own task, to see what is a stroboscope. Stroboscope. This is your task. You just see from internet what stroboscopes do. Clear? I cannot explain it because time is too short to explain all these things. Okay, mass to be top in the moving through equilibrium position. The corresponding amplitude is 21.6 mm. So the amplitude, we call it x, is 21.6 mm. If an unbalance of each wheel of an exciter is 0.0921, so unbalance, as I told you in the last lecture, unbalanced means ME. Remember, M into mass into small mass into eccentricity distance is 0.0921 kg meter. So unit is kg into distance. Determine, so we have to find natural frequency, the damping factor, which is zeta. Zeta called damping factor, damping ratio, same thing. Its amplitude at 1200 rpm when you change omega, and the angular position of eccentrics at an instant structure moving up is the angular position means you have to find theta, which means the force, the phase angle between the force, because exciter creates a force. So eccentrics is basically these masses which are rotating that are generating the force. So we have to find theta. If it's a pre-resonance, the theta is less than 90, as I told you in the last numerical. If it greater than 90, so if it is post-resonance, the theta will be greater than 90. You'll see in this numerical. Now in the first part, you have to take, this is very important to understand. Now in the machines where the mass is more than 100 kg, vibration amplitudes are of the order of few mm, or you can say not greater than 5 mm. Clear? So what I am saying here, that you see the amplitude here as mentioned is 21.6 mm. Now this is so high amplitude for a so heavy machine, which is 181.4 kg, that you consider to be a resonant amplitude. I am again repeating, that's very important. By the way, when the problem is given numerical, this numerical is actually from a book and statement is slightly vague, but I just give a criteria based on my training with the industry, that when you have heavier mass machines which are more than 100 kg, amplitudes are order of few mm. Sometimes it's 1 mm or 2 mm. Now, but 21.6 mm, which is roughly 2 centimeter, is a very high amplitude, and generally when this amplitude occurs in the machines, it is a clear indication that the system is resonating. That's why you have to consider this amplitude as a resonant amplitude. Okay. Again told you, whenever I give you numericals in the exam, this is slightly a vague statement, but in the exam I will clearly indicate you that the amplitude is so high that maybe the word resonance may be given, or maybe you will easily see that there is a resonance. But I give you a criteria, and just to keep in your mind, when machines have a mass greater than 100 kg, the amplitude are generally small, which is 1 or 2 or 3 mm. If you see amplitude rather than 10 or 15 mm, you can conclude easily that maybe a resonance is coming into your system. Now, when you see this, then you have to take omega over omega n equals to 1, because this is what resonance is, or omega is equals to omega n. So, because your RPM is now 900, and you know what omega is, which is 94.2 radians per second, so that must be your omega n. Clear? So I think by using the relation, now see, it's an unbalanced mass, so its ME is coming. So now the first thing is to find natural frequency. So natural frequency comes out very clearly, which is 94.2 radians per second. Because if we consider it as a resonance, and in a resonance, because omega is equals to omega n, so whatever the value omega is, omega n come out to be the same. Now we have to find the damping ratio. So for the damping ratio, you see X resonance is instead of now using this relation, because we know now we have an unbalanced relation, so we then use, if you remember, ME over capital M into omega by omega n whole square divided by square root of 1 minus omega square over omega n square whole square Clear? Now, don't worry, these formulas are given in your exams. So, idea is not to actually try to remember those relations. They are given. You have to just use it. Okay, when you say resonance, so this goes to 1, this goes to 1, which means this goes to 0, and this also goes to 1. So you end up with ME over capital M 1 divided by, again this is only 2 zeta here. Now, because in this system, if you look at, we have the imbalance of each wheel. Each wheel means now we have 2 wheels. So total unbalance is, so instead of like ME, we write 2 ME. Why? Because we have 2 wheels now. So total unbalance is 2 times ME. As again written in the numerical, that in the unbalance of each wheel of an exciter. So we have 2 wheels, one is this, second is this. So we have 2 wheels. So these 2 wheels creates the 2 unbalance, which is 2 times ME. So in this relation we have to write 2 ME divided by capital M. So we are interested in zeta. So XRES is equals to, so ME divided by 2 M cap zeta, and the zeta is nothing but ME divided by 2 XRES into capital M. Now instead, because you have 2, so you have to write 2, because we have 2 wheels. So it will come 2 into 0.0921, which is the unbalance of each exciter, into 2 into, okay, what is the amplitude, resonant amplitude, which is 21.6 mm. So 21.6 into 10 to the power minus 3, because you convert into meters, multiply by 181.4. So zeta will come out to be 2 into 0.0921 divided by 2 into 21.6 exponent minus 3 into 181.4. See, it's 0.023. So it's an underdamped system. Clear? Now the third thing is find the amplitude at 1200 rpm. Now whenever something is changing, so it's omega. Remember, you can't change omega n. Omega n cannot be changed unless you change stiffness and the mass. So omega is now, in the third case, the omega is now 1200 rpm. 1200 means it's 12 multiplied by 2 pi divided by 60. So 1200 multiplied by 2 pi divided by 60, you get a value of 125.7 radians per second. Now because you can't change omega n, as I told you previously many times, so omega by omega n is 125.7, and what is omega n? It's 94.2. So 94.2. So 125.7 divided by 94.2, you get a value of 1.34. So see, 33. So see, it's a post resonance. How we don't know that? Because the value of omega over omega n is greater than 1. Now we consider that whatever your theta come out to be, that should be greater than 90 degree. Okay, before that we have to find the amplitude, and amplitude is nothing but again me over m, and again it's 2 times because we have 2 unbalanced masses, divided by omega over omega n whole square, divided by 1 minus omega square over omega n square whole square, plus 2 zeta omega by omega n whole square. This is our relation. So just putting the value, this is 2 into 0.0921 divided by what is capital M, which is 181.4. What is the frequency ratio? It's 1.33 square divided by square root of 1 minus 1.33 square whole square plus 2 into what is zeta, 0.02 into 1.33 whole square. So if you solve this, so it becomes 2 into 0.0921 divided by 181.4 into 1.33 square. So you get the value of 0.00179 divided by, so if we solve the square root, so 1 minus 1.33 square whole square plus 2 into 0.02 into 1.33 square. So you get a value of 0.77. So 0.00179 divided by 0.77, you get a value of 0.0023 meter, which is 2.3 mm. Now just compare it. When your RPM are 900 and the resonance is occurring, the amplitude is about 21.6 mm. But if I slightly increase the omega, which is now from 900 RPM to 1200 RPM, so see, amplitude is almost decreased by 10 times, which is now only 2.3 mm. That we're telling you that at resonance the amplitudes are generally very high. So if we slightly increase omega, so that the amplitudes now only become 2.3 mm, and that is very much in the range where the system can be operated. Okay. Now the last thing that is left is only your theta. So theta is tan inverse of 2 zeta omega by omega n divided by 1 minus omega square or omega n square. This is what the zeta is, So tan inverse of, so 2 into 0.02 into 1.33 divided by 1 minus 1.33 square, you get theta equals to 2 into 0.02 into 2 into 0.02 into 1.33, which is the frequency ratio, divided by 1 minus 1.33 square, two into 0.02 multiplied by 1.33 divided by 1 minus 1.33 square. So you get a value of tan inverse of minus 0.069. And if you get tan inverse of minus 0.069, so value is coming out to be very small, which is minus 0.07 degrees. So not degree, it's radians. Clear? It's radians. If you multiply 0.07 into 57.3, so you get an angle of roughly minus 4 degrees. So minus 4 degrees means you have to minus it 180 degree. So you get a value of 150.76 degrees. So that is see, it's a post resonance. It's a post resonance. And why multiply with the 180? Because 180 is the maximum difference between the, so if it means that when your eccentrics is at the top, your mass is actually at the bottom. Clear? Which means at the bottom extreme position. So the maximum angle can be 180. So if we got a minus sign with the angle, you have just subtracted 180, you get the plus, which is 176. That clearly indicates that it's a post resonance. So it's your problem 3.13 from exercise, and same is the problem, which is problem, and you have to solve it yourself. That is your example 3.2, 3.1. The same course exciters, the varying the speed of resonant. Now there it is written resonant amplitude is 0.6 centimeter, which is about 6 millimeter. So again, as it written as resonant, so there is no need to verify whether it's when the speed is increased beyond considerably, resonant frequency amplitude approaches to a fixed value, 0 determine the damage. So to find zeta. So it's a one relation. I think you now you can solve yourself with enough understanding of those numericals. So now moving towards the next numerical, which is, I think, is taken so long. So this is again you have to solve yourself, because we have to solve other two numericals. So just give you a hint of solving this numerical. So you have to solve yourself. So the a balanced wheel supported on spring. So we have this is a wheel which is balanced, and this is a spring, is rotating at 1200 rpm. So the wheel, so its omega is 1200 into 2 pi by 60, whatever the value is. Now a bolt weighing 15 grams, so generally what happens is, not mentioned here, but if you look at the car or wheel, so it has 4 bolts, sometimes 6 bolts, sometimes 5 bolts. So they are located at equal distance from the center, so that the total mass center is actually aligned with the rotational center. As I told you in the last lecture, that what we want is that the center of mass should be on center of rotation. That is our main purpose. if only one bolt flies off, it creates an unbalance. So say it's a bolt of 15 grams, so ME, which is the unbalance, is 15 grams multiplied by 5 centimeter. So it's nothing but 75 grams centimeter. This is the unbalance, because one bolt has flied off, now created an unbalance. So ME is 75 gram centimeter. So if you convert gram centimeter to kg meter, 75 into 10 to the power minus 3 into 10 to the power minus 2. Okay? So that will become 75 into 10 to the power minus 5 kg meter. Clear? This is your unbalance. So now it says if the flies off, determine the build up of vibration. If the natural frequency is 18 CPS with a damping ratio, so zeta is 0.1, and 18 CPS means your omega is 2 pi f, which is 2 pi, and because it is written CPS, so cycles per second, so multiply with 18. So your natural frequency come out to be 2 into pi into 18, and that is 113.1 radians per second. Clear? Now the main idea you have to determine the build up of vibration. Now this word is very important. Build up means you have to find x of t. Build up means how vibration are developing up. And remember, whenever it's written, either it's written the vibration response, you have to find x of t. It is written vibration build up or development of vibration, so it's x of t. In other numerical, maybe it's you find the zeta, or maybe find the frequency ratio, or maybe find the amplitude. But if it's written find the response of the system, or maybe find the build up of vibration, you have to find x of t. And x of t, if you remember, is all but equals to E minus zeta omega and t. So do not remember this free vibration, because it's involved in the build up of vibration. C1 sine of omega dt plus C2 cos omega dt, and because it's an unbalanced case, we have to use the unbalanced relation, which is capital ME over M, omega by omega n whole square, sine of omega t minus theta divided by square root of 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Just for the sake of your understanding. So you have to find x of t. Now in this there are two unknowns. So I'm just giving you a hint, you have to solve yourself. The only unknowns are C1 and C2. The rest are the known. ME is known. Okay, if the capital is not known, then keep it capital M, because T is also not known. But you have to write this relation, all the values that can be find out. So omega d is omega n under root 1 minus zeta square. So that you can find from the above values. Now the only hint that I can give you are the initial conditions. Because there is no specific initial condition to this, because you have not displaced the system, you have not applied a certain shock. So if you take both initial conditions equal to 0. This is what the hint is. So use this relation, it's a one relation, use both initial conditions, try to find, and just one more hint, that for sake of simplicity, take this whole factor take this whole factor as some q value, some constant q, so that your numerical squeezes, because you know it's a constant quantity and you cannot involve in derivatives. You can find the value of q from the values given, and then using the derivatives, so just derivate. So just in next case, so first, so if you know first initial condition is 0, So you put x of t is equals to x of 0, put all t is equal to 0, find that C1 and C2 or combination of C1 and C2, and then take the derivative of this, the previous equation, this equation. By second simplicity, put the whole equal to q. You can find the q separately because you know m is known. Okay, capital M is not known, but take it as capital M. Omega by omega n is known. Why? Because omega is 1200. So omega is 2 pi into 1200 divided by 60, whatever the values, and divided by omega, and you get the ratio. Omega n also given. So take the derivative, find this. So using both these equations, you can find C1 and C2. This is your purposes, and then at the final you write x of t, which is some lengthy. This is what you have to solve yourself, and maybe this kind of problem will be given in your exams. So it's my humble request to kindly solve it. That's why I'm giving you some clues, so that you are not actually do not start from scratch. You know exactly what you have to do, and based on this solve yourself, because these are very important numericals. This is from your book. Now in the last two, because we have now solved so many numericals, we have to solve two sample problems, and that is I have designed myself for your better understanding. And apart from those two numericals, also give you two other numericals, the solution, so that you have a more better understanding of. Now this is a sort of a design problem. Now it says there is a camera here and there is a small mounting bracket here. See? So it's a bracket, it's a camera. A security camera is to be mounted on the building top and will be subjected to a continuous wind load. Now what happens is, because it's a tall building, and what happens is when a wind flows over that camera, it creates vortices behind it, and these vortices causing that camera to vibrate. Clear? Or maybe in this direction, or maybe in the inward direction, okay? In the other direction. So if I take the cross section of camera, so it can be vibrating like in this direction, or maybe in this direction. Okay, when the peak force measured is 20 newtons. So we measured the peak force. So the F naught, which is the peak force, is 20 newton. That is the peak force of the wind. The wind frequency is about 12 hertz. So frequency, so this is not Fn because this is a wind frequency, and wind is the external force. So it's F. So it's 12 hertz. So you can find omega from here. Omega is 2 pi F, which is 2 into pi into 20. You get, not 20, sorry, 2 into pi into 12. You get a value of 75.4 radians per second. This is for omega. I said it's not omega n. Why? Because it's a wind frequency, and wind is an external source. Clear? The camera mass is 2 kg. So m is 2 kg because the camera is your main mass and bracket is your stiffness. Okay, the mounting bracket is made of aluminium with square cross section. So this bracket is made of aluminium with square cross section. So if you look at the cross section square, clear? So its dimensions are 20 mm by 20 mm. Ignoring damping, so we use zeta equal to 0. Determine the desirable length of the mounting bracket. So we are interested in finding the length, which is this, so that the vibration amplitude remain equal or less than 5 mm. So that the amplitude remains less than or equal to 5 mm. This is a kind of a design problem. Clear? Again, we have to use the same formula because of forced vibration, because wind is flowing. Now take modulus of elasticity. So E for aluminium is given, which is 69 gigapascal. Okay. So use the same relation. So just because we are interested in amplitude, so because there is no unbalance, there is only force, so you write general relation F naught over K divided by square root of 1 minus omega square over omega n square whole square plus 2 zeta omega by omega n whole square. Clear? Now because we are ignoring damping, so zeta equal to 0, so relation will only remains f naught over k divided by 1 minus omega square over omega n square. Clear? This is our final relation is. Okay. Now the most important thing, just hold on. Okay, in this equation, the most interesting thing is that you have to find the length of the bracket. Now, just use your slight understanding of what we have done last time, where the lengths come into this formula. This is your formula, where lengths come into the formula. Now, length is associated with the bracket, and the bracket has some stiffness, so it has some k. So, see, you will certainly realize that it comes in the natural frequency formula. So natural frequency is under root k by m. Now this bracket is like a cantilever beam with the end mass. Now see, for a cantilever beam, the k is nothing but 3ei over l cube. And if you're slightly confused, I'll just give you an idea that these will be given in your exam. So don't confuse it. But the main idea that you have to understand is where you get those formulas, how do you apply those formulas. So you can now see that your relation become f naught over k divided by 1 minus omega square over omega n square. Now omega n is nothing but under root k over m, and k is nothing but 3ei over l cube. Clear? So there are many different ways to solve the problem. The one way is try to solve this problem by first finding omega n. You can also put the value of k and then find the L directly, but maybe it becomes slightly complicated. So what I'm using the approach is, so you say if you take square on both sides, so it become omega n square equals to k by m. So k is equals to m omega n square. So putting this value here, so x equals to f naught over m omega n square divided by 1 minus omega square over omega n square. So using this relation, I will try to find the value of omega n. It is slightly, you have to use slight mathematics to do that, but we will do that in this numerical. Now x is, because the numerical says it's less than or equal to 0.5 mm, sorry, so you can take it at the value. You can, because it's less or equal to, so you take 5. If in the numerical it is given it's less than 5 mm, you can take 4, you can take 3, you can take 2, 1. Don't take 0 because then everything will be 0. Take the value less than your desired value, which is 5. Now because it is less or equal to 5 mm in this numerical, just take 5. So but mm, so you have to put 5 in 10 to the power minus 3. Instead of writing in the 10 to the power minus 3 form, just write 0.005. Okay, so f naught is, I think so, given, which is 20, divided by m is 2 into, now omega n square is remain as it is. 1 minus, so omega is, we have find out to be 75.4, so 75.4 square divided by omega n square. Clear? Now if you take this because okay, cross multiply it, so 20 will be divided here and 2 and omega n will be multiplied here, so what you get is 0.005 into 2 into omega n square divided by 20 equals to 1 over 1 minus 75.4 square divided by omega n square. So just multiply in the above 0.005 into 2, you get 0.01 divided by 20, you get 0.0005 omega n square equals to 1 over 1 minus 75.4 square divided by omega n square. So if I take the inverse on the both sides, so we get 1 over 0.0005 omega n square is equals to 1 minus 75.4 square divided by omega n square. You can use any other approach, I have no problem at all. Just to but you can say an approach to solve it. You can even put the values of k and can find directly omega n. So if you take this, if you divide 1 divided by 0.0005, you get a value of 2000. So 2000. So if I take this on the left hand side, what you get is, so just write here so that you never miss the step. So 2000 divided by omega n square plus 75.4 square divided by omega n square equals to 1. Yeah. So it's equals to so 2000, again write the step, divided by omega n square plus 4 square is nothing but 5685.2 divided by omega n square equals to 1. So because base is same, denominator is same, so you can add 2000 plus 5.2, you get the value of 7685.2 divided by omega n square equals omega n square is equals to 7685.2. So omega n is nothing but under root, so it's 87.7 radians per second. This is your omega n. Now you know that omega n is nothing but under root k by m, and you know that k is nothing but 3ei over l cube m. Now we are interested in the l, so if we take square on the both sides, you get omega n square is equals to 3ei over l cube m, and l cube is nothing but 3ei over omega n square m. If we take the cube root on the both sides, so l is nothing but cube root of 3ei divided by omega n square m. Now I is equals to, because it's a square cross section, so I is equals to BD cube by 12. So B is 20 mm, we are converting to meters, so 20 to 10 power minus 3 meter. The D is also 20 to 10 power minus 3 meter. Okay, if it is rectangular cross section, then the direction they may become very important, in which direction it is bending. So it is given when you have a different values, but because of square cross section, it can be in any direction. Okay, the I will so I just write the next steps here so that all steps are visible on this page. So I is equals to now 1.33 into 10 to the power minus 8 meter 4. So I is given, the E is given, you can find, I think so, E is 69 into 10 to the power 9, the I is 1.33 into 10 to the power minus 8, omega n is now 87.7 and m is 2 kg. Just put those values, you get length is equals to 0.57 meters. So it means your at least your length will be 57 centimeter. If you want amplitude of less than 5 mm, it can 5 and even larger, because the image can distort. Generally, if we take the amplitude should be less than 0.1 mm to get the exact image, so it should not distort. So even the length can be smaller than if you take a small amplitude, you can say range. Okay, so we are moving towards the last numerical for this lecture, and I hope we have solved so many numericals, so you have more understanding of what we are doing. So last numerical is numerical sample problem 2. So this is again a slightly different, but more or less the thing that we are doing it before. So it says an unbalanced disk rotating at 900 rpm. Now we have an unbalanced disk, which means there is a slight sort of unbalance, and balance, as we know, is nothing but me. So rotating, so omega is because it's an unbalanced, so it's omega, it cannot be omega n because it's unbalanced disk, which creates a forced vibrations. So 900 rpm into 2 pi divided by 60. So 900 into 2 pi divided by 60, you get 94.2 radians per second. This is what omega is, with a machine of 600 kg. So m is 600 kg because the machine is horizontally installed on the floor with the help of 4 springs and 4 dampers. So now what happens like this, so if you just take this as a 3D diagram, so this is, let's say your machine is actually here. It can be some lathe machine, or can be a milling machine, or can be any type of machine. So we have at 4 corners, we have 4 springs and dampers. Okay. So I have seen this assembly in the HIT, where they have installed the test bench of the tank engine using 8 springs and dampers. Okay. So this is quite common in the installation of the, and similar is the case here. Okay. So we have 4 spring and dampers on each corner of the machine, and they are parallel. Each spring has a weight of 2 kg and a stiffness of 25 kN per meter. In most of these numericals, we ignored the effective mass of spring because the numericals become more and more complicated and difficult to solve. Okay, the accelerometer installed on the system. The accelerometer generally is used to get the vibration data. The accelerometer installed in the system generates a vibration signal from which the approximate value logarithmic decrement is 0.24. So we take the logarithmic decrement 0.24 because from the values of sensor and the amplitude ratio we get the value of 0.44. Now if an unbalanced force system recorded by a load cell, so unbalanced force, which is F naught, which is unbalanced force of recorded, this load cell record the force to be 500 Newton with respect, okay, when the ballast mass is at the extreme position with respect to horizontal axis, and if the system is excited with the initial velocity of 100 meter per second. Now if the system is initially excited with the velocity of 100 millimeter per second, which we, so initially means it's initial velocity determine the time dependent response of the system. So see, it's the same numerical if you remember from which we have seen with the tire, wheel. So it's the same sort of numerical. Just hold on. So I will solve it completely so that even for the solving that wheel numericals you can easily understand. Okay, so so we have now the initial velocity is known. We know all other parameters F naught. Now in unbalanced force, the F naught is equals to me omega square. If you remember our modeling, we have done me omega square. So me is the unbalance, which is written, I think so, Okay, so our balance is not written, but me omega square whole value is written. So there is no need to write me only. So total force is given. So we know x of t, which is a complete response, is nothing but so instead of using C1 C2, I'm using this relation for free vibration. So don't confuse. I've told you you can use both. This is your free vibration. Now in force vibration, because there is no me given, so you can directly use this relation, because you now know the. Now remember, there is no problem of using both relations. Both are fine. If your me is given separately, it's some 0.1 kg meter. Now it's instead of unbalance is written as force, so you can use direct relation to that. The good way of solving it is okay. We have two initial conditions because there is no displacement. So x of 0 is equal to 0, but x dot of 0 is 100 mm per second, or in other words you can say it's 0.1 meter per second. So initial velocity is given. Okay, now the good thing is, instead of solving this taking derivative, you can first find the values and just put those values, so that you actually relation becomes slightly easy. How? See that. So we know what zeta is. Zeta is delta over under root 4 pi square plus delta square, as we have seen in the lecture of dam free in logarithmic decrement. So logarithmic decrement is 0.44 divided by 4 pi square plus 0.44. So I will given the solution of this numerical, specifically this, only this to you, so that you have a better understanding. I will upload the solution. So this will be equals to 0.44 divided by square root of 4 pi square plus 0.44 square. You get a value of 0.07, and that is again tells you it's an underdamped system. Now as you can see that we have a 4 spring and 4 dampers. So so we have found total zeta because we have taken a signal of the sensor, so it has actually reflected the damping of all 4 dampers, but because the spring are present on the 4 corners, so we have to add the stiffness. The total stiffness is K1 plus K2 plus K3 plus K4, and both springs have an equal stiffness, so it's 4 times K, which is 4 times, what is the stiffness? It's 25 kilonewton per meter. So it's 100 kilonewton per meter. So what is the natural frequency? It's under root K by M. So the total spring is 100 into 10 power 3, which is 100 kilonewton, divided by what is the mass of the machine, which is 600 kg. You get a value of, so your natural frequencies come out to be 12.9 radians per second. This is your omega n. Okay, what are the values known? So you can find the whole factor. Instead of, you can find the whole factor. Instead of writing the formula, we can write the whole factor. Okay, the omega is given, which is 94.2. So what is omega by omega n is 94.2 divided by 12.9. So you get 94.2 divided by 12.9. You get a value of 7.37. So its ratio is very high. So when your omega n is very high, so it generally means your amplitude is generally on the smaller side. This is what we have seen in the last lecture. So as told you in the last lecture, that in most of the cases we want that omega by omega n should be greater than 3. That is best for your system because you have a very small amplitude, as we have seen in the graphs. Any other value known? Okay, zeta is known, omega n is known. Okay, omega d. Omega d is omega n under root 1 minus zeta square. So it's 12.9 into under root 1 minus 0.07 square. So square root 1 minus 0.07 square into 12.9. get a value of 12.86 radians per second, very close to 12.9. Okay, so now we have to find, okay, we call this factor to be q and just find the q factor. So q is f naught over k divided by the whole factor, just writing the, do not writing the whole relation. So it's f naught is, it's recorded is, okay, f naught is 500, total stiffness is 100 × 10⁻³ divided by 1 minus the, this is 7.3 square whole square plus 2 into what is zeta is 0.07 and this is 7.3 whole square. So just in the case there is no need to write this relation and again. So 500 divided by 100 exponential 3, so you get 0.005 divided by 1 minus 7.3 square whole square plus 2 into 0.07 into 7.3 square, 52.3. So 0.005 divided by 52.3, you get a value of 0.000096. So see, instead of or you can take, okay, equals to 0.0001. Okay. So see, it's very small factor. Why small? Because you know, when you have very large omega, generally these factors are very small. Okay, so x of t is some x, we don't know what x is because initial conditions, minus, okay, zeta is 0.07 and omega n is 12.9. So we get 0.9 t sine of what is omega d is 12.86 t plus phi, both are unknown, plus, okay, so we know the factor which is 0.0001 into cos, and what is omega? Omega is 94.2 t minus, okay, you can also find theta, and theta is, just write theta here. So theta is tan inverse of 2 zeta omega by omega n divided by 1 minus omega square over omega n square. So just actually putting the values, so 2 into 0.07 which is zeta into omega by omega n which is 7.3 divided by 1 minus 7.3 square, you get minus 0.01, taking tan inverse of this you get minus 0.02, so theta is equals to minus 0.02 radians. So you multiply it with 57.3 or pi by 180 by pi, you get minus 1.1 degrees. So theta is equals to 180 minus 1.1 degrees, so it's 178.9 degrees. So see, it's basically the post resonance. As you can see, the theta is greater than 90 degree. So clearly it's a post resonance. Okay. Okay. So it's the value can be written as 178.9 degrees. Okay. Now we know two initial conditions. So we are interested in finding x and phi to get the final response of the system. Okay. So two initial conditions are x of 0 equal to 0 and x dot of 0 is equals to 0.1 meter per second. So putting the first initial condition, just writing with the blue color. So the first initial condition, you get x of 0 is equals to capital X and e power is 0 is 1. So sine of 0 plus phi plus 0.0001 cos of 0 minus 178.9 degrees. This becomes 0. So you get 0 equals to x sine phi plus 0.0001. So if you multiply cos, so convert into radians. Okay, so cos of minus 78.9 degrees, you get a value close to minus 1. So you get into minus, okay, sorry. Plus 0.0001 into minus 1. Okay? So you get x sine phi is equals to 0.0001. This is what the first relation is come out to be after putting the first initial condition. Okay, now putting the second initial condition. So for before that we have to take the derivative of this x dot of t. If you take the derivative of this term, so you get x, and this is minus 0.9 e minus 0.9 t sine of, this is 12.8, okay, omega d is 12.86, yes. So it's 12.86 t plus phi, okay, plus 12.86 into e minus 0.9 t cos of 12.86 t plus phi, okay, minus, okay, what is 94.2 into 0.0001, so you get 0.0094, so just write it clearly, 0.0094 into sine of 94.2 t plus, sorry, not plus, minus 178.9 degrees. Okay, this is what it comes out. Okay, if you put the values of, okay, so again now put x dot of t equals to 0.1, sorry, x dot of 0 is equals to 0.1. So just writing here, just to see, this goes to 1, this goes to 0, this goes to 1, this goes to 0, this goes to 0. So you end up with x into minus 0.9 into sine of phi plus 12.86 plus 12.86 into cos of phi minus what is minus sine of 178.9 close to 1, this is close to 0, so sine of 178.9 3 okay, it's point close to 0, it's 0.02. Okay, so sine so 0.0094 into it's sine of minus 178.9 divided by 7.3. Okay, it's minus into minus, so what is the value of sine of minus 178.9 degree? It's multiplied by 0.0094, so you get the ultimate value of plus 0.0002. okay, so x is, if you put x value is, x is equals to 0. So we take at x equals to 0.0001 divided by sine phi. So 0.0001 divided by sine phi, I multiply, it's minus 0.9 sine phi plus 0.0001 divided by sine phi into 12.86 cos phi plus 0.0002. So this is cancelled with this sign, is cancelled with this sign, so you get minus 0.9 into 0.001, so you get minus 0.00009, so you get a lot of zeros here, plus 0.0001 into 12.86, you get 0.00128 cot phi plus 0.0002. So you can now say that 0.000128 cot phi is equals to, if take both terms on the left hand side and just subtract it, so get 0.1 minus 0.1 plus 0.0009 minus 0.0002. okay, so it's equals to 0.009989. So cot phi is divided by 0.000128. So you get 780.4. This is cot phi, and what tan phi is, you can take the inverse of it. So 1 divided by 780.4, you get 0.0013, and phi is equals to tan inverse of 0.0013. You take tan inverse of 0.0013, so get answer of 0.00 in fact 13 radians. It's a very small angle. So if you multiply it with 0.0013 into 57.3, so you get answer of 0.07 degrees. This is what the value of phi is. This is what the starting angle is. Okay, so what is x now? So x is 0.0001 divided by sine phi. So 0.0001 divided by sine, and because we have set calculated in radians, so you just put the value in radians, so it's 0.0013. So x is nothing but 0.001 divided by sine of 0.00013. You get answer of 0.077 meter, in fact, which is 70. So it's okay, just wait a minute. So it's 0.0013. Okay, the answer is 0.077 meter, which is 777 millimeter. 1, 2, 3. Okay, there is something wrong in the calculations. So or 0.0013. Okay, yes. Okay, so it's basically 0. Okay, you have to just solve it again if you find any problem in that. So it was 0.0077 meter. Clear? So it's 7.7 millimeter. Clear? So x of t is nothing but now 0.077 sine of 86. Okay, what is that value? Oh, 12.86, sorry. So it's 12.86 t, and what is phi? Phi is 0.07 degree plus 0.07 degrees plus, and what is Q factor, which is 0.0001, 0.0001. So sorry, this value, sorry, I'm again mistaken. This value is 0.077 meter. Yes, 0.7. Okay. 0.0001 cos of 94.2 T and minus what is theta, that is 178.9 degrees, minus 178.9 degrees. So this is your total response. So whenever it is written, this is your total response of the system. Now yes, we have seen about, I think so, 6 or 7 numericals.